Okay, we're going to start today. Little review since we met last week. We're in Chapter 9, Compressible Flow. We were talking last time about converging nozzles, and we worked a couple problems on that, and that's where we are today. So today we're going to kind of shift gears of sorts and look at an important topic in compressible flow, which is going to build on what we're going to do on maybe later today, probably Wednesday. Shock waves in flow fields. Shock waves, the official definition here, irreversible discontinuities. They can occur in a supersonic flow field. That gives you a big hint right there. They occur in a supersonic flow field. They may. They can be either internal or external. I think we're all familiar with external shock waves. There's pictures of aircraft shock waves online that shows in certain weather conditions it can show the shock wave off the aircraft body. They can also occur inside of pipes. They can also occur in nozzles, which is where we're going to see them in our class. They can be standing, like in a pipe or a nozzle, or they can be moving, like a fighter jet going Mach 1.2. Okay, their discontinuities tell you something. That means there's a sudden change in something, a discontinuous change in something. The reason why it's pretty much discontinuous, first of all, is their thickness. Is on the order of 1 times 10 to the minus 5 inches. So they're very, very thin. And across that very thin shock wave, dramatic things happen. So big changes in properties across the shock. Accelerations, tremendous accelerations. If it's air, the molecules of air go through tremendous decelerations across a shock, So the first thing to do is to look at the shock wave and analyze it from our basic equations in fluid mechanics. So we'll start off and we'll look at a shock wave here, and let's say it's contained in some kind of a duct, in this case a constant area duct. Our control volume is the dashed lines. Approaching the shock wave, we have conditions 1. Leaving the shock wave, we have conditions 2, other side of the shock wave. We'll talk about upstream of the shock wave. This is upstream. Downstream, that's downstream, like in a river. Upstream, where the water comes from. Downstream, where the water goes from to. So upstream, downstream. First of all, we have conservation of mass. This is steady flow, okay? So we have rho AV at 1 equal rho AV at 2. But the areas are the same, so continuity rho 1 V1 equal rho 2 V2. the area on both sides is essentially the same because it's so thin. 1 times 10 to the minus 5th inches. All right, that's conservation of mass. Now we have momentum. And we'll call that in the x direction. So our momentum equation, the forces, pressure forces on both sides, because the mass flow rates are the same, m dot 1 equal m dot 2 from continuity or conservation of mass. You don't need a subscript on those guys. They're the same. Then we have the first law, thermal energy. We'll use the form H1 V1 squared over 2 H2 V2 squared over 2. H enthalpy. Enthalpy. Then we have the equation of state for a perfect gas. P equal rho RT. And we also have for this the change in H2 minus H1 for constant C sub P is equal to C sub P T2 minus T1. That's constant C sub P. So basically those are the equations we're going to work with. There's a lot of stuff going on. In those equations, you can count the unknowns. Five unknowns. You assume the upstream conditions are given. So you assume you know all the subscripts 1. Rho 1, T1, P1, H1, V1. The unknowns are the downstream values of those unknowns. Okay. Conservation of mass, momentum, energy, equation of state, constant C sub P. 1, 2, 3, 4, 5. So the object is to solve those 5 equations for those 5 unknowns. So you go through that, and we end up with a number of equations. I'll just write a couple of them down here. Let's do the P2 over P1. Now, these guys are all going to be K1.4 because pretty much that's what we're going to be looking at. I'll tell you what to do if it's not K1.4. But for right now, it's going to be K1.4. Okay, so you solve this guy for P2 over P1. Okay, P2, P1, P right here. You get that equation. Let's take another one. Let's take T2 over T1. So we go through that, and what we try and do is we try and make the right-hand side only a function of Mach number, because the Mach number is going to be the important dimensionless parameter, the Mach number. So the right-hand side of all these guys are going to be expressed in terms of the Mach number. Okay, we got the temperature. M1 squared plus 5, 7 M1 squared minus 1 divided by 36 m1 squared. Right side's only a function there of Mach number. Rho 2 over rho 1 is equal to 2.4 Mach number 1 squared divided by 2 plus 0.4 Mach number 1 squared. It can also be shown that that's the same thing as V1 over V2. Flip-flop the subscripts. One subscript's numerator, two subscripts denominator. So now we have, so far, four expressions. One gives you P2, one gives you T2, one gives you rho 2, one gives you V2. Okay, now if you want to find the Mach number 2 squared, Mach number 1 squared plus 5 divided by 7 Mach number 1 squared minus 1. That's going to give us the Mach number 2 across the shock wave. Now, if you do that and look at the results, I'll put the variable here, and I'll put the change across the shock wave here. Okay, Mach number. Static pressure. Stagnation pressure. Static temperature. Stagnation temperature. Density. Velocity. Entropy. Those are all the properties we're typically interested in, and the velocity and Mach number. Okay, here's what happens across the shock wave. Change across the shock wave. Mach number goes down, decreases. Static pressure increases. Stagnation pressure decreases. Static temperature increases. Stagnation temperature does not change. Density increases. Velocity decreases. Enthalpy increases. You can show that by plugging numbers in the equation. I'm sorry. Entropy. Yeah, I'll mention it in just a minute. If K is not 1.4, okay, K is not 1.4, then we're going to use equations 955, 958, and 959. So those equations just have K and the Mach number 1 here. It has K and the Mach number 1 here. It has K and the Mach number 1 in the equation. It has K and the Mach number 1 in the equation. Only difference is you'll see a K in all the equations. So put the right K in. Only use these guys here if K is 1.4, and I showed you before all the gases that have a K of 1.4. There's a lot of them. Now, when you solve these 5 equations for these 5 unknowns, you're going to get 2 values of V because it's squared. When you take the square root, you get 2 values of V. Now, with those 2 values of V, the textbook goes through it. If you put those in the change in entropy, one gives you a positive change in entropy and one a negative change in entropy. Now, the shock wave is irreversible. So you can guess from your thermal background what entropy does. It doesn't go down. It goes up. It goes up. Irreversibility cause entropy to go up. Therefore, you choose the right V that causes the entropy to go up, okay? And that's reflected over here then. Entropy, of course, must increase across a shock because of the irreversibilities in the shock. Like what? Well, friction. Friction, major irreversibility in a shock. You got freeway jam-packed, everybody's going 70 miles an hour. One guy in the lane up there decides, he sees a part of a tire from a truck in the lane. He puts his brake on. Everybody puts their brakes on, but there's going to be a massive collision. Everybody's going to slow down. They were going 70, now they're going 10. Velocity goes down. Because of the collision, what happens? The cars get hotter. Why? Because of metal on metal friction. Yeah, same thing here. Big collision, molecules going really fast. They hit the shock wave. Ooh, their velocity decreases. Slowly. Oh no, read it again. Discontinuously. Within a small area. Yeah, same thing. That's why these guys behave like, that's why he goes up, he goes down, things like that. Okay, so what you want to do, you're in the compressible world. Chapter 9, number 1, you have no intuition. You don't live in a compressible world. You don't go Mach 1.2. But everything you've got in the world is based on that. Okay, so what do you do then? This. Believe the equations. They're the truth. They're the truth. I don't care what they say. Say, that doesn't seem right to me. Oh, yes, it is. That's because your intuition isn't right in a compressible world. So these things may seem strange to you. They do. Of course they do. But that's okay. You're in a new world. Turn the page over. Incompressible? Compressible. Intuition? Won't work. Equations? Yeah, they work fine. Now, you can use the equations if you want. Or if you want, you can go to table B2. Okay, I'm going to put them both down again just to contrast them. So let's see, table B1. Okay, here it is. Let's put down table B1 first. Isentropic. Okay, so we have our table B1, a Mach number. And we have P over P naught. Rho over rho naught. T over T naught. A over A star. Okay, we start out at 0, 1, 1, 1, infinity. We go down to a Mach number 1. We go down to a Mach number 2. It goes all the way down to a Mach number of 4 in your textbook table B1. It goes down to 4. Okay, table B2. Shock table. Table B2 in the back of your book. Mach number 1. Mach number 2. P over P2 or P1. P2 over P1. Row 2 over row 1. T2 over T1. P naught 2 over P naught 1. Last column, A star over A star 2 over A star 1. Mach number starts out at 1. It goes to 2. It goes to 3. And let's double check it just to make sure. B2. Yep, stops at 5. Okay, I'm not going to show it. Just we've done fine up there, so it stops at 5. Okay, so put some numbers in. 1, 1, 1, etc. If the Mach number upstream of the shock is 1, it's reached sonic speed. The Mach number downstream of the shock is also 1. Is there a shock? Yeah, but it's very, very weak. Very, very weak. It's there, but it's very, very weak, okay? Now go to 2. If the upstream Mach number is 2, the downstream Mach number M2 is 0.5774. Wow, the Mach number really went down. It's subsonic now. Mach number, right there, decreases. 1, less than 1, decreases. 3.4752. Wow, it's getting smaller. Conclusion. The higher the Mach number on the upstream side, the lower the Mach number on the downstream side. Shocking stuff, isn't it? Oh, that's right. That's why it's called a shock wave, okay? Yeah, that's why. Don't try and figure it out. Say, I don't understand that. Don't worry. Don't worry. You don't live in a compressible world, Mach 1.2. But here's the conclusion from the equations. This guy goes up, this guy goes down, right there. Now, just so you remember from your first fluids course, this is the static pressure. This is the stagnation pressure. What's the stagnation pressure? The pressure at a point in a flow field where the velocity of the fluid comes to rest isentropically. Okay. T naught. T, no subscript. Static temperature, T naught. Stagnation temperature. Stagnation temperature on a reentry nose cone where the velocity comes to rest. Do you think it gets hot there? Oh, you better believe it gets hot there. It gets really hot there, okay, because of friction. Even without that, bring it to a rest without friction, it's still hot. Let's see, I got that guy. Okay, we've done this guy. We've done the row. Okay, not the row yet. Okay, row. P2, let's do the P2. P2 is 1 here, 4.5. Down here, 10.33. Okay. Let's say the pressure upstream of the shock is atmospheric pressure, 14.7 pounds per square inch. What's the downstream pressure? Oh boy, is it really big. 10.33 times that. Will it blow your eardrums out? Probably, yeah, probably. Don't stand on the deck of a carrier with a jet over at Mach 1.8. Your eardrum will be blown out, yeah. Why? Because that pressure increases so dramatically. Pressure goes up, let's check it out here. Static pressure increases, yes it does. Okay. Density 1. Density at a Mach number of 2. The density is 2.6667. 2.6667. Okay. The density increases. Oh yeah, the density, yeah, it increases from 1 to 2.667. How about the velocity? It's just the reciprocal of the density. So the change in velocity is 1 divided by 2.6667. What is the density went up? What's the velocity do? Here it is. It goes down. What's the Mach number do? It goes down. I'll put 3 on there, 3.8571. The temperature, Mach number of 2, the temperature ratio right across there, 1.6875. At Mach number of 3, temperature 2.6790. Did the temperature go up? Oh yeah, the temperature. What temperature? The static temperature. Yeah, static temperature. P naught 2 or P naught 1. Okay, P naught 2 or P naught 1. 1. Okay, Mach number of 2. There we go, 0.7209. Mach number of 3, 0.3283. What did stagnation pressure do? It went down. Yeah, stagnation pressure down, yeah. That's where that list came from. Put the numbers in. How come it went down? Well, this is a measure of how much energy that the flow has. It takes energy to cross that shock. It takes energy to push those molecules through the shock wave. They want to resist that. So that change in energy is used for the fluid to go across the shock wave. So the energy of the fluid decreases. See, one goes down, one goes up. You think, oh man, what's going on here? Okay, there it is. Don't say what goes on here, say, I believe the equations. Okay, repeat it yourself 10 times. I believe the equations. Don't get too involved with it. Well, I don't understand why, I'm confused. No, that's all right. Of course you'd be confused. This is a compressible world again. And a shock wave is even worse as compressible. Okay, we'll get this guy later, but for right now, just so you know, there's also an A star 2 and A. Let's go back, what's the star conditions mean? It means the location where the Mach number equal 1, the location where we have sonic speed in the flow field. Okay, 2.0, 1.3872. At 3.0456. No, it's 3, okay. 3.0456. you can go on down. It goes on down to 5 in the table. Mach number 5, hypersonic speeds. Now, in the table, you won't see some things. Stagnation temperature. You won't see a T01 over T02 over T01. Why? Because it doesn't change, stagnation temperature. So there's no column titled T02 over T01. You won't see the equation up here for this A star, but it's in the textbook. It's rather long, so I'm not going to put it down here, but I'll just tell you that there's an equation in text. Okay. So there are all of the, there's the equations. This is for K 1.4. If K is not 1.4, use these guys. Here's the shock tables, this guy. Here's the isentropic tables. Okay. And of course, what happens across a shock is right here. Okay, so I think that's all we need to do an example problem. So I'm going to work that, I think, over here. I'll keep this on here. Okay, example. A normal shock the shock wave is normal to the velocity vector. That's why it's not, normal because there's something, he's a normal guy. No, it means it's normal too, okay? Now, the other side of that is some shock waves go off like that. That's called an oblique shock wave. The angle is not 90 degrees. That's for the advanced group. Save that for a graduate course if you're a mechanical engineer. Aerospace people discuss that in their classes, of course, but usually we don't in a quarter type course. So we're just going to be looking at normal shock waves in our class, normal shock waves. There's other ones in the real world called oblique shock waves, but we're not going to be concerned about oblique shock waves in this class, just a normal shock wave. Okay, now let's go back to here. A normal shock stands in a duct. It's not moving, it's stationary. Believe it or not, that happens sometimes. And that's in chapter 9. But the normal shock wave is staying there. It's also in our next topic, which is shock waves in varying area ducts. Okay. Let's get some properties down. P1, 10 psia. T1, 40 degrees Fahrenheit. V1, 2190 feet per second. Okay, find downstream conditions. Okay, find the downstream conditions. Now, first thing, I think I might have mentioned it, but I'll say it again. You can't have a shock wave unless you have supersonic speed. To have a shock wave, you've got to have Mach 1 greater than 0. If the Mach number is 0, there really is no shock. It's isentropic. It's isentropic here over here. So M1 has to be above 1. If it's 1, they're all the same. M2 equal M1, da, 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 da. You've got to have supersonic Mach number in order for there to be a shock. Okay, so we expect that. Okay. First step, all of these tables and equations have a Mach number in the first column. Mach number, first column. Mach number 1, first column. Mach number in the equations. Conclusion, if I can find the Mach number, I can do a lot of stuff. Okay, so the first thing you do is try and see if you can find the Mach number. Okay, I want to find Mach number 1. M1 equal V1 over C1. Good, I know V1. 2190 divided by the speed of sound in a perfect S, the square root, KRT. If I do that, I get 2190. We went through the British gravitational system before. We know what R is, 1716, K is 1.4. Be careful. Temperature, you've got to add 460, of course. Everywhere, it's got to be the absolute temperature, not the relative temperature. The absolute pressure, not the relative pressure. That's absolute, PSIA. We know in fluids, you've got to be very specific. You don't just say the pressure is 10 PSI. No, that's not good enough. I don't know what you mean. Do you mean gauge or absolute? You can ask the guy at Jiffy Lube, make sure my tires are up 32 PSIA. The guy says, pardon me, did you say 32 PSIA? I said, yeah. I said, what does that mean? Oh, I'm sorry, just 32 PSI is okay. See, we speak different language. We have to be very specific. So we say PSIA. If you tell somebody the pressure is 200, let's say 2,000 and 214 kPa. Now don't forget, let's say the pressure is 32 PSI in your tires, okay? And you want the absolute 32 plus 14.7, and this is gauge, and this is PSIA, okay? Now, if this is absolute and this is, let's say this is gauge, and this is absolute at 101, is there such a thing we speak about? The pressure is 214 kPags. The guy says, huh? kPag? What's a kPag? I'm sorry, it's 315 kPa. Say, kPa? What's that? You know, here's the deal. In British gravitational, we're very specific. We put an A and a G after the PSI. In SI, here's the rule. They don't use A and G. If you see kPa, you're supposed to assume that's absolute. That's the rule. And if it's gauge, you might want to do this. Or in words, say the gauge pressure is. So in SI, it's kPa. That means absolute. You want gauge, you say kPa, parentheses gauge, or say the gauge pressure is 315. If flip-flop those guys around, it should be gauge up here and absolute here. Okay, just so you know the language we're speaking here, okay? Everything's got to be an absolute, whether it's temperature or whether it's pressure, absolute. Okay, back to here. We put that in there, 1095 is equal to exactly 2.0. Yep, I made up a good problem, 2.0. So, there we go. Here's table B2, shock table. I got it, that's my entry point. So let's get the T2. T2 is equal to, over there, temperature, static temperature, 1.688, round off. T1, 500, so 844 degree R. Or if you'd rather, equation right here, plug them in, get T2. Get the pressure downstream of the shock. 4.5 P1. Yep, 4.50 P1. At pressure, 45 psia. Okay, T over T naught. T over T naught. I want T naught. There he is right here. T over T naught. 0.556. Okay. That's right there, 0.556. Yep, that's it. I didn't put Mach. Oh, yeah, that's what I did right here. So that is 0.556. So T naught, T1 over 0.556, 900 degrees R. P over P naught, 0.128. At 2, there it is. Yep, 128. So P naught equal P1 over 0.128. P1 was given 10 psi. So P naught 1, 78.1. P naught 2. Okay, I want P naught 2. Here, right here. P naught 2. Mach number 2, 0.721. P naught 1. Okay, put these guys on here. Put him in there. 56.3 psia. T naught 2 equal T naught 1, didn't change any. Stagnation temperature does not change. T naught 1, 900. Find V2. V2 equal, let's see, V2. Here it is right here. Okay. Where do I have my V2? It's the reciprocal. V1 over V2 right there. So I get my V2 equal V1. From the table, I get 2.667, which gives me V2. I know V1, 2190. Gives me 822 feet per second. Let's get row 2. Row 2. You can do it one of two ways. If you want to find row 1 first, then use the ratio here to get row 2. You can find row 1. P over R, P1 over RT1. Do I know P1? Yep. Do I know R? Yep. Do I know T1? Yep. But I'll get P2 this way, row 2 this way. So we have row 2, P2, RT2, P2, 45, 144 square inches per square foot. R, 17, 16. T2, I just found T2 up here. T2, there it is up there, 844. Row 2. Slugs per cubic foot. And you can't, that's all. You can't find anything else. That's enough. We did everything. If you don't want to read the table, use the equations. B2, B2, B1, B1, B2, you know it. B2, there's a table you use. Okay. Okay, so that's how you go across a shock wave to get all those different properties. Now, the next thing is these shock waves can appear in some nozzles. That's our next topic, is shock waves in nozzles. Okay. Okay. This goes out to some large back pressure region. This is the exit plane. This is the reservoir. Flow goes through here. We discussed it before. You can never reach supersonic speeds in a converging nozzle. It's always going to be subsonic or at best sonic at the exit plane. It could be, but it'll never be supersonic. You could reach Mach number of 1 at the exit plane, but never greater than 1. Conclusion, no shock waves. Okay, so we don't have to consider a converging nozzle with shock waves. It's not going to happen. Now, our next thing, and we talked about this before too a little bit, a converging diverging nozzle. Okay, so now converging, diverging. Okay. So we start off the same way, reservoir, P naught, T naught. We go into a converging portion of the reservoir. We come out of there into a diverging portion of the nozzle, and we exit to a back pressure region. This is the exit plane. This is called the throat of the nozzle. This is called the reservoir. Very, very large area. Okay, so there's different cases in a converging, diverging nozzle. Let's take, we'll plot it here, I guess. That might be the best way to do it. So here is our pressure ratio. We had the converging one, now we have the diverging one. So this is our P over P naught. And they normally call this the X direction. And they call this the exit plane. And this is the throat. And this is X equals 0. If there's no flow, if the back pressure equals the reservoir pressure or vice versa, there's no flow, nothing to cause flow. You need a difference in pressure to cause flow. Okay. Now you start lowering the back pressure. Okay, you lower the back pressure. It says, okay, P0, I've lowered the pressure back there. And so the fluid starts to flow. We're going to take air because air is so common. So air starts to flow. Okay. The pressure goes down, goes through here, and comes back up here. I'm not going to, the textbook puts A, B, C, D's by them, but I'm not going to do that. You lower the back pressure still more. This is the back pressure out here now. This is P back over P0. You lower the back pressure, and it comes down here. It goes up here like that. More flow goes, that's more flow. You lower, I'm going to go through, take this curve I just drew, Mach number in the reservoir 0, Mach number 0.1, 0.2, 0.3, 0.4, reaches 0.4. Subsonic 0.4. 0.3, 0.2, 0.15. Okay. Mach number went up, Mach number went down. Okay. Now, we reduce it some more, and we get down to, if K is 1.4, 0.528. Magic number, the Mach number is now 1 at the throat. Mach number 1. And then it goes back to subsonic because the pressure is up here. Now I want to design a supersonic nozzle. So here's the supersonic designed converging-diverging nozzle. That line. We talked about that before. That's called the supersonic design converging-diverging nozzle. So if you want supersonic flow at this point right here, there's your little model aircraft. You want Mach number 1.5 there? Then you want to be on this curve right here. You want to get Mach number right here, 2.5. What's a Mach number here? 1.0. What's a Mach number here? 0.5. Okay. And we stopped there last time. We said, okay, there's a big gray area there. We don't know what's going on there. What if the pressure is here? Any of those little tick marks on there? What happens there? Okay, here comes the shocks. You go through Mach 1, the flow becomes supersonic. Could there be a shock? Yeah, there can be a shock because a shock has to be occurring as supersonic flow. Yeah. So what happens is there's a shock there, and it goes back to there. Or if the pressure is reduced some more, you go down here. Now there's a shock here. You go back to there. They're getting bigger and stronger. The shock waves are getting stronger as you get more and more supersonic. As you get more and more supersonic, that pressure goes up dramatically, the density goes up dramatically. Yeah, it's getting stronger and stronger. You reduce the pressure some more. There can be a shock wave at the exit. At the exit plane, there can be a shock wave right here. I'm going to erase this, but I'll just show you. That's this picture right here. The shock wave is sitting at the exit. Now, there's a blank area here, okay? What happens in this blank area here are oblique shock waves go out like that. And there's a blank area down here, which is typically like expansion waves out there. We're not going to discuss those guys. Those are for advanced topics. So in this region where the shock is at the exit, then the shock gets kicked out of the exit and it becomes an oblique shock. Or if the pressure is reduced below the supersonic design nozzle conditions, then an expansion wave occurs outside the exit plane. We're not going to discuss those guys or those guys, okay? This one here, oh yeah, that's the supersonic design converging diverging nozzle. Is the exit pressure equal to the back pressure? Yes. Is the exit pressure equal to the back pressure, even if there's a shock wave there? Yes. Is the exit pressure equal to the back pressure? No. If the shock sits there, the exit pressure is down here, the back pressure is up here, the answer is no. So there's the complete roadmap, okay? Subsonic everywhere, subsonic everywhere, subsonic to the throat, Mach number 1, subsonic back here, subsonic here, supersonic here, subsonic there, subsonic here, supersonic here, subsonic there. You've got to understand the road map, because that's going to tell you which table to go. If you see a shock wave, use table B2. If you're in a region where there's no shock wave, use table B1. If I'm on this curve right here, table B1, got it. If I'm on this curve right here, table B1, shock is 1.0. It's no shock, it's 1.0. This curve right here, table B1 to here, table B1 to here, table B2 across the shock, table B1 to here. That's the road map. Once you get the road map down, life becomes easier. Okay, so let's go ahead and look at, this is a rather lengthy problem, but we'll get started on it and we'll continue on it next time. All right, I'm going to draw the picture over here. Converging nozzle, no shock waves. Maximum Mach number in a converging nozzle, Mach 1, is possible at the exit conditions only. Okay, do I want to keep that up there? Maybe I will. Yeah, I'll keep him up here. Okay, here's the example. Okay, so we have air. The reservoir conditions, let's see, P naught 300 kPa. Temperature 500 Kelvin. Flow goes through the converging, diverging nozzle. There is a shock wave in the diverging part of the nozzle. We're given that the areas, I think I'll put them right here. Okay, I'll put over here. Area of the throat equal 1 square meter. Area 1, I'll show you one in just a minute. 2 square meters. Area at the exit, 3 square meters. Okay. So we're given that information. Okay. I'm going to call this 1 and this 2. Sometimes some books will do this, and that's fine too. If there's the shock wave, they might call this 1 upstream, U, and 1 downstream. That's okay too, but I like the 1 on the tube. Either way is fine, just so you know, different ways to do it. Okay, back to here. I got a shock wave. Oh, right there I am. That's it. That's my roadmap curve. Now I know what I'm on. I can erase everything else. It's always good to figure out where you are because this stuff is tough enough. So take every advantage you can. If you can do it without the roadmap, that's fine. But most people need help. That's what I'm on. Is P exit equal to P back? Yep. Because I'm on that curve. I told you why before. Did I reach Mach 1? Of course I did. Did it go supersonic? It had to. There's a shock wave there. All right, here to here. Here, Mach number 0. There, Mach number's 1. Subsonic. Once it patches the throat on this curve here with the shock wave, it has to go supersonic until the shock supersonic. Once you go across the shock, table B2 tells you it's subsonic. Okay, so now you know that part of it, what's going on. Okay, so now you say, okay, so from here to here, let me think. Is there a shock between those two arrowheads? Nope, there's no shock. What do I do? Table B1. Okay, across the shock, what do I do? Oh, I know. Table B2. Between the downstream side of the shock, what's the Mach number there? Subsonic. Oh, subsonic. B1. Table B1. Now you've got a really good idea of where you are and where you're going. That's a key. Once you do that, you feel much more confident about what you're going to do. But without that, and all those equations and all those tables, I guarantee you, it's very easy to be totally confused. Okay, I guess I didn't put out what we're supposed to find. Okay, find P1, P2, P02, P03, T3, T03, PB, M dot. Oh, I could ask a ton more, but I'll stop there, okay? That's enough. There's 3 positions, well, there's 4. The throat, 1, 2, and the exit. Anything with a subscript T is the throat. Subscript 1 is before the shock. Subscript 2 is after the shock. Exit plane is subscript E. In this case, exit condition here is the back pressure. Okay, we'll just start and do 1 or 2, then we'll come back and finish this next time. Okay, since there's a shock, I know Mach number at the throat equal 1. Got it. at location 1. A1 over A1 star. A1 is equal to 2. A1 star. Now, A1 star is the location, is the area at the location where the Mach number's 1. Mach number's 1 at the throat. Area of the throat, 1. Okay. Why do we need to put a subscript on A star? Isn't A star just A star? No, if there's a shock present, A star changes across the shock wave. So you've got to do your bookkeeping really carefully. This is A1, this is the area A1 star. Anywhere from here to here, my 2 fingertips, A1 star, A star in that region, A star is 1 square meter. Between my 2 fingertips, A star changes. Okay, so one value of A star is good here. When you go across the shock, you get a new A star, which is valid anywhere between my 2 fingertips. Okay, so now I know A star 1 and A star 2. All right. A star 1, pardon me. So now I'm going to go over here to my location. You can use the equation, you can use the tables, it's your choice. I'm going to find the Mach number at 1. Mach number at 1. Okay. Okay, what do I use? Here's your road map. Okay, table B1. Table B1, got it. Okay, go to table B1. B1 here. Look for A1, look for A over A star of 2. Look for A over A star of 2. I'll show you where it is. There it is right there. Why'd I go there? You know the rule. There's a picture, road map. You got the road map, life is easier. Okay, what do I want? I want to find this guy. Go across here, find him. 2.20. Okay. Mach number at 1 equal 2.20. It's supersonic. Of course it is. Look at my road map. Where my finger is. Supersonic. Got it. Now I want to find P1. So next. P1 over P naught 1 is equal to. Okay. Where do I go? Table B1, it says it right there. Go to table B1, I got it. Mach number 2.2, got it. I want to find this value right here. So that value 0.0935. Okay, so yeah, 0.0935 gives the static pressure upstream of the shock 26.08 kPa. Got it. PO1. PO1, 300. Anywhere that my pen point is, I don't care where I am, P naught is equal to 300 kPa. Here at the throat, what's P naught? 300 kPa. Just before the shock, what's P naught? 300 kPa. It doesn't change until you go across the shock. Okay, haven't crossed the shock yet. Okay. If you want to find, I didn't do it, you could find T1. I didn't say find, I could say find P1, T1, row 1, da 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 da, V1, anything, tons of stuff. I'm just doing some of the stuff for you. Okay, good stopping point. There's more to go next time on Wednesday, so we'll see you then on Wednesday.